Okay, this is Data Structures and Algorithms, Unit 5. This unit is about graphs. We talked about graphs a little bit with binary trees because that kind of helps to put it under that umbrella, but now we're really going to finish that conversation. So our first lesson is on adjacency matrices and searches, or another word for search we're going to give is a traversal, okay? So a graph is an abstract data structure. We've been studying abstract data structures this whole course, composed of nodes and edges. The edges can be directed or undirected and can be weighted or non-weighted. So let's look at the following undirected, non-weighted graph. So weighted graphs will have on the edges, they'll have weights corresponding to the cost of traveling upon those paths. The nodes themselves could also be weighted. So you can have weighted edges, weighted nodes, all sorts of things. The edges can also be directed, meaning that instead of having an edge like that, they have an arrow, which indicates only one direction of traversal. So this is the data structure as we picture it in our mind and on paper, but it's very different than how it's, actually made. So the way this graph can be represented is as a matrix. The nodes that share an edge between them are called adjacent nodes. So you want to be careful about a couple of things about adjacent nodes. One is that if the edge is undirected, then each node is adjacent. So here in diagram 1.2, you can see that A is adjacent to B and B is adjacent to A. However, with a directed edge, we would say that A is adjacent to B, meaning that you can get to B from A, but B is not adjacent to A. So we would say that you cannot reach A from B. And you need to be careful with this idea that just because something is not adjacent, it doesn't mean it's not connected, because we could still get from A to B from somewhere else. We're just saying that they're not adjacent. They're not you can't get there without going through somewhere else. All right, so we're going to describe this graph using an adjacency matrix. We can use true and false. We could use the weights themselves using infinity, like the math dot infinity value from the double. All sorts of things to indicate not connected. I'm just going to use 0 for not connected and 1 for connected. So A, do we say that A is connected to itself? Well, we're actually not. We're going to say no on that one, okay? Because there's not like a loop like that. If there were, then I would say A is connected to itself. But A is connected to B. So I'm starting on this row. By the way, these letters here, of course, in when you're coding it, will not be there because you'll just be making a matrix. Let's see here. We'll say A is connected to C. A is connected to E, and nowhere else. Now we go to B. B is connected to A. B is not connected to itself. B is not connected to C, but it's connected to D, and F, but not E. C is connected to A, not B, not itself, not D, but it's connected to E and F. D is connected just to B and F. E is connected just to A and C. And F is connected to C, B, and D. And there we have it. We have an adjacency matrix. So believe it or not, this here, when you see this matrix, you think this graph. All right, the number of edges from a node is called its valence. If all the nodes in a graph have even valence, then we'll say the graph contains an Euler circuit. In other words, the graph can be traversed in such a way that every edge is traveled exactly one time and the path begins and ends at the same node. So finding Euler circuits or creating them through a process called Eulerization is actually extremely important in lots of different applications. Let's take a look at this graph here again and see if we have an Euler circuit. Well, you can note that valence at A, that is the number of edges coming out of A, is 3. That's an odd number. And it turns out you actually can't have, you're always going to have an even number of odd number valence in a connected graph. So I've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So I got 4 nodes that have a valence of odd. So this does not have an Euler circuit. There's no way I could start at A and travel along every edge without having to repeat. So if this was like a mail delivery, and these are streets, and along these streets there are different mailboxes, where our postal service employee is going to have to traverse some street more than once. You're going to have to backtrack somewhere. And the process of Eulerization would be adding an extra edge representing backtracking to where you do it the minimum amount of times. Famously, the Israeli nation went through a process of Eulerizing their public works, like mail and trash service, and saved like billions of dollars. I don't know, back in the 90s or something like that. It was made news. Okay, so that's Eulerization. That's Euler graphs. A graph in which a walk can be constructed from a specific starting node to other nodes and back to the starting node without repeating an edge or a vertex is said to have a cycle. So lots of graphs have cycles. We have this graph here has this cycle here. Has another cycle here. A big cycle, and then another one here. So cycles are, gosh, I could do even more. We could say like here, 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 here. So this graph has a lot of cycles in it. A graph that has no cycles would be called a tree. We've seen those before, right? A graph in which every node can be reached from any starting node, either directly or by passing through other nodes, is called connected. So this graph is connected. If I'm on any one of these nodes, I'm not stranded from reaching somewhere else. And a digraph that is connected in its directed state is called strongly connected. So those are some different vocabulary words that we'll come across. Oh, and weakly connected is a digraph that's connected when an undirected graph is laid over it. So it's like, ooh, it would be connected if you could travel both directions, but we call it weakly connected. All right, what we're going to do is we're going to construct some adjacency matrices, and we'll describe each one of these as whether or not they are connected or not. We'll state whether or not at least one cycle exists. Okay, so let's go ahead and do that. All right, I've got 1, 2, 3, 4, 5, 6. So I'm going to make a matrix of 6 different nodes. So we'll say A, B, C, D, E, F. All right, so A to A is 0. A to B is a 1. A to E is a 1. Everything else is a 0. B goes to A and C, but everything else is a 0. C goes to E and B, and everything else is a 0. D goes to F. E goes to F. Oh, no, E goes to A. Sorry. E goes to A and C. And F goes only to D. This graph is not connected because you can't get to D or F without having started over there. It does have a cycle right here. That's a cycle. So it's not connected, but it contains a cycle. All right, let's do this one. We have A, B, C, D, and E, and I'll label them down here. A, B, C, D, and E. And the instructions say that if we have this loop, we're actually going to label that with 2 so that we can actually check valence very quickly for Euler circuits. So that's just kind of an added little trick, because when you have a loop, you actually have, that counts as 2 edges. So 0, 1, 0, 1. Let's see here. This is 1, 0, 1, 0, 1. C is no. B, yes. Itself, 2. D, 1. And E, 0. D goes to A, C, and E. And E goes to B and D. Okay, this graph has lots of cycles, and it is connected. All right, now we get to look at one that is a directed graph, so a little bit different here. A, B, C, D, A, B, C, D. So from A, I can get to D, and I can get to B, and nowhere else. From B, where can we go from B? Well, we can go to C, but that's it. We can't go back to A. From C, we can go to nowhere. From D, we can go to C, and that's it. One of the points out, notice that out of our answers we've had so far, this is the first non-symmetrical. It's kind of hard to read my handwriting, but note that all these matrices have to be square just by definition because you're going to have the same rows as columns. But they're all symmetric across this diagonal. Do you see that? All symmetric because they're not directed. But when they're directed, then you lose that symmetry. Okay, this graph here is weakly connected, but it's not strongly connected because if you start at C, you can't get everywhere. All right, let's take a look at this next one. We have A, B, C, D, E. A, B, C, D, E. All right, A is not connected to itself, but it's connected to B and D. B is connected to A and C. C is connected to B and E. D is connected to A and nowhere else. And E is connected to C and nowhere else. Okay. Now that we know how to represent them, let's talk about how to traverse them and search them. So a depth-first search and a breadth-first search. We need to know how to use both of them, but here's the thing. If you recall how to write iterative searches of binary trees, you basically already know how to do this. In fact, it's even easier than that. So a depth-first search can be implemented using recursion or a stack. I'm going to be using a stack pretty much all the time. So that's pretty much the only difference in these two algorithms is whether you use a stack or a queue. If you use a queue, it'll be a breadth first search, meaning you look all around you first. If you use a stack, you'll be looking depth first, which means you'll go down as far as you can into the graph before you come back. So basically, let's start with A, and the algorithm is pretty simple. You push the starting node on the stack, and that makes your stack just the letter A. Then while the stack is not empty, you pop, visit, and push all the unvisited nodes adjacent to the current pop node that are currently on the stack. Okay, so, and what order that you choose to add them in, we can do them alphabetically. It doesn't matter. It's still going to search everything. So we have a stack. And we're going to have a list of visited nodes. This could be easily just like a visited array. So I'm going to go A, B, C, D, E, F, and G. And I'm just going to make these are going to be all false, okay? Because we haven't visited them. And so we've also got our adjacency matrix, and the index in your visited array would correspond to the position of the row of your adjacency matrix that you're using. So let's start with A. We're going to put A on our stack, and I'll call this, you can talk about it visiting, or maybe we're searching for a specific element that's stored there. So we start with A, and what we do is we pop it off the stack. So pop A off the stack. Boom. We visit it, which means this is no longer false. This is now true. And we're going to push on the stack everything that A is connected to. Now, how do you do that? Well, you have to go to the adjacency matrix for this thing and go to A's row. So what you're really pushing on these stacks are indices in your adjacency matrix. So we've got A, B, C, D, E, F, and we've got, A, B, C, D, etc. And so what I'm really pushing on this stack here is the index 2, because that tells me 2 is what I'm going to be pushing on that stack. Then when I pop it off, I go to that row and I look through that row in the matrix to find something that's a non-zero. And when I find it, I push that column number onto the stack if I haven't visited it. But we'll worry about that more later. Let's just get the idea down. Okay, so now that I'm done with A, I pop off the stack. So pop off the stack comes at the bottom, because remember you stack the last thing you put on is the first one to come off. And there's nothing to visit, but there's nothing to add to it, so I'll just mark that as true. Then we'll pop off the stack, and we'll add to our stack F and G. And we will mark that we have now visited visited C. Okay, and that's gone. Then we're going to pop a G off the stack. After popping G off the stack, we can mark that G has been visited. We'll take everything that G is connected to, which is nothing, and then we'll pop off the stack. We'll get F, and we'll make F true. And we'll be adding to our stack B and D. And then we'll pop D off the stack and visit it. Nothing to add that we haven't already visited. We might try and add B again, but we've already visited it. And then lastly, we'll pop B off the stack, and that will be visiting all of them. And that completes our search. A breadth first search is quite similar. You just use a queue. So again, I would offer A to the queue, and then I pull A, and I offer everything to the queue first. And I would offer E and C. And then when I pull from the queue, or C and E, I would pull from the queue, I'd pull from the top. So I grab C, and I would add to the queue G and F, or in this case F and then G. And then I pull from the top and I grab the E, and nothing to add. And it goes on, and I'll spare you the details of going on that. But what the difference is that while a depth first search, depending on the order that you do it, might take C and then F and then D and then backtrack and check B and then backtrack and check G and then finally backtrack to E. The breadth first search will always search what's directly next to it first before going on. Like that. They both kind of look like a breadth first here in our example, but that's the difference between the two. Okay. I do have just a couple of typed up algorithms here that we can look at. So here's the depth first search algorithm. You create a stack of integer values representing the row index of the nodes in the adjacency matrix. Then create an array of Boolean values called visited, where the index of the array is the node number and the values indicate if that number is visited yet. Push the starting node's index into the stack, and then while the stack is not empty, pop a node off the stack, visit the current node, add all of its adjacent nodes that are neither in the visited yet, which have been neither visited yet in the already, they can't be already in the stack to be visited. You don't want to add them twice. The only difference between that and a breadth first queue is this word right here, queue. Exactly the same algorithm. Okay, and there's a dot contains for stacks and queues in your because they're a linked list. All right, so that's pretty much it for that lesson. I want you to, download the Graph Viewer program from my webpage, and the Graph Viewer will allow you to, if it will load, I'd like you to first play around with this matrix here and see what happens. See what happens when you try and delete one. And you'll see, I think red means it's only coming from red. Whereas if it's symmetric, it would be black. So this blue one is indicating arrows. Arrows were difficult. So, so you can play around that and make the different graphs that appear. And then we're going to do a graph traversal viewer and a graph DFS viewer. So we're going to really try and analyze how these things work out.